Computers can actually think in ways people never could, so this isn't scientists just getting lazy. Aside from being able to hold more information than a person could learn in many lifetimes, one of the key strengths to a computer is its ability to look at large amounts of detail in a short window of time without forgetting something or making an error. This allows them to make detailed simulations and models. Previously, a lot of biomolecular knowledge would read something like, if we introduce more glucose to the cell, the production of X, Y, Z hormones, molecules, or enzymes will increase. With advanced simulation and modeling on computers, we might see something more quantitative. As Altaf Ul Amin et al. State in their research paper on systems biology, computational methods add a numerical character to topics that would otherwise have been vague and general when handled by traditional biology. X amounts of glucose added to a cell will produce specific amounts of chemicals, X, Y, and Z, over a specific time frame. Computers allow us to create a scenario in order to see exactly what is happening, not just speculate on trends. There are a couple of ways that computers are going to work in biology. The first is more statistical. The technology to generate massive amounts of data emerged before the ability to process it. So researchers really have millions of gigabytes of information sitting around waiting for somebody to do something with it. This data includes details about cells in many different scenarios. There's information about concentration of different chemicals and enzymes during different times and conditions. There is genetic information about different kinds of cells from different people during different conditions. A scientist might want to know what a certain enzyme does. He might say, we have thousands of scenarios where our mystery enzyme exists in differing amounts based on different conditions. I wonder what the relationship between the presence of the enzyme and the presence of alcohol is. He could run hundreds of scenarios through the computer and find that when alcohol enters a cell, mystery enzyme starts to go away. What if the relationship wasn't that simple? What if mystery enzymes started to disappear when alcohol was present, glucose was low, and another known enzyme was within a specific range? There are a lot of different chemicals and enzymes that can exist in a cell, and it would take a long time to analyze the relationships between every combination. That's where computers really shine, because they can compare multiple relationships at one time, faster than a person could, and they do it automatically. This is referred to as systems biology, because biologists are looking at entire systems of cells rather than just one cell. This way, we can spot general trends that hold true for the entire body, or relationships that are more complicated than 2 or 3 molecules in one certain scenario.
It's an impossible and huge project to understand not just the elements of biological systems, the genes and the proteins and so on, but how they are integrated together. And therefore it's vastly bigger in terms of scale than just sequencing the genome. That was vast enough, of course. Putting it all together is going to be very much more difficult. Some people say it's impossible. I say it's not impossible, it's imperatively necessary in order to understand.
The other utility of computers in biology is the ability to simulate things that we don't already have data for. Drug developers in the pharmaceutical industry would love it if they didn't have to drop random chemicals into big vats to see if it made something useful. Fortunately, they don't have to, because they can drop virtual chemicals into simulations and see what the computer thinks is likely to make something useful. In a journal article published by Nature, Vivian Marks refers to this kind of testing as in silico, and it can save organizations enormous amounts of money. Biology really isn't the only field where computers are becoming noticeably more important. Business, finance, education, and entertainment are all seeing big roles for computing, and most other fields are seeing it at least a little. When it comes to big data research in biology, there is hardly a difference between a computer expert and a biology expert. How could a biologist run detailed simulations if he didn't know how to use a computer? What would a computer scientist run simulations on if he didn't understand biology? As time goes by, the fields of science are becoming interdisciplinary. simply because they're all so useful. Why only have sociologists study sociology, when one could also bring in a physicist? They're both brilliant in different ways. There's a clear advantage to using both kinds of brilliance to solve problems. As Watt says in his book 6 Degrees, if it is to succeed, therefore, the new science of networks must bring together from all the disciplines the relevant ideas and the people who understand them. The science of networks must become, in short, a manifestation of its own subject matter. That's what bioinformatics is all about, bringing two schools of thought together to create something better than both of them individually.
That person.
So it will be a science of systems. In the case of the biologist, we can call it systems biology. In the case of medicine, we can call it systems medicine. And in the case of the way we teach it and the way it happens in the private sector, what that translates into is a biologist sitting next to an engineer, sitting next to a physician, sitting next to an ethicist, sitting next to an information theoretician or computer scientist, sitting next to a statistician.